We turn our attention now to line integrals of vector fields. I'll set it up and then we'll draw a comparison to other line integrals that we've seen. If we consider a curve in R3 that contains a point P sub I star, which has coordinates xi star, yi star, zi star. Like the diagram that we saw in R2, that would be this one. And we saw this when we were first setting up line integrals. So we have a curve C, and this time we're envisioning it in R3. And we have a point P sub I star that has x, y, and z coordinates. And represent the unit tangent vector P sub I star as t of t sub I star. Then we can consider t of t sub I star delta s to be an incremental distance along the curve C. And rather than drawing a diagram, I have one from the textbook. And here we have a delta s here going from p sub I minus 1 to p sub I. And within that interval here, we have p sub I star. And at that point, we have the unit tangent vector t of t sub I star. Now, F is a vector field actually, and F is the force that is moving a particle from P sub I star to P sub I. Considering T of T sub I star times delta S as a distance, and F, the vector field, as a force, the work done in moving a particle from P sub I minus 1 to P sub I along C is the sum as I goes from 1 to n of F of x sub I star, y sub I star, z sub I star dot t of t sub I star times delta S. In other words, work is force times distance. So the vector field F is the force doing the work, and then the other part is the distance along C. And since F and T are both vectors, this multiplication is a dot product. Taking the familiar limit process, we get that work is equal to the line integral over C of F of x, y, z, that's the vector field F, dot T of x, y, z ds, which is abbreviated line integral over C of f dot t ds. Here we have the arguments just so we can see that we're in R3. Using vector notation for the curve, r of t is equal to x of ti plus y of tj plus z of tk. Doesn't really look like a j. And using that t of t is equal to the magnitude of, r prime of t divided by its magnitude, and the fact that the magnitude of r prime of t is ds dt, we get that this expression for work is equal to the integral from a to b of f of r of t dot r prime of t divided by its magnitude times r prime of t in magnitude dt. To see the connections from above, f was given as f. Whoops. R prime of t divided by its magnitude is the unit tangent vector. And then r prime of t in magnitude dt is ds. Since the magnitude is a scalar that then divides out, we end up with w is equal to the integral from a to b of f of r of t. And what that's saying is that f has been, the inputs for f have been parameterized. But we've got f of r of t dot r prime of t dt which can be written as the line integral over c of f dot dr. That is an expression we are going to see an awful lot. Now I'd like to compare this line integral that we've just written with what we saw in a previous video, namely that a line integral of f is given by the integral from a to b of f times the magnitude of r prime dt. Here I haven't written f of xy or f of xyz because I don't want to tie it into 2 space or 3 space. It's the same expression either way. The point here is f in before, when we first saw line integrals, is a scalar function, and the magnitude of r prime of t is a scalar function. And so this is regular multiplication. Here now we have f a vector field, and r prime of t is a vector. And so the multiplication is a dot product. That's an important distinction to make. We have to use the correct multiplication for the function that we're starting out with. And we'll know when we see it, because not because of a lowercase or an uppercase f, but because f of xyz is either going to have real value outputs, or you're going to see it in vector notation. Now I'm going to summarize by bringing in a definition. Let f hat be a continuous vector field defined on a smooth curve C given by a vector function r of t for t going from a to b. Then the line integral of f, that's f hat, along C is the integral over C of f dot dr, which is the integral from a to b of f of r of t, which is a parameterization of the curve C, dot r prime of t dt, which is equal to the integral over C of f dot t ds. So here we have f is the vector field. The curve C is given by r of t, t going from a to b. And then, of course, our familiar ds here. I'm actually going to include the TDS here so that we can just join everything together there. Now we'll tie this into some notation that we saw before. Suppose that f hat is given by pi plus qj plus rk. So we're saying the components of f are just labeled p, q, and r. Then the line integral over c of f dot dr is equal to the integral from a to b of the dot product of p, q, r with dr, which is going to be x prime of t, y prime of t, z prime of t times dt. That can be, well, simplifying gives us the integral from a to b of p of x, y, z, x prime of t plus q of x, y, z, y prime of t plus r of x, y, z, z prime of t dt, which can be then expressed as the line integral over c of p dx plus q dy plus r dz. And so we can see that the line integrals respectively with respect to x, y, and z actually sum up to become f dot dr. And now for a quick note. The line integral over a negative c of f of x, y, dx is equal to the negative of the line integral over c of f of x, y, dx. The negative in front of the c here in the first case means that the orientation is reversed from the original curve c. And what this says is reversing the orientation has the effect of giving us the negative of the line integral. And that's because if we reverse the orientation, the sign of dx reverses as well. Likewise for y, and also z in the case that we're in 3 dimensions. But reversing the orientation of c for a line integral with respect to arc length, so f of xy ds, has no effect on the sign of the output because ds is defined to be something with a square root. And so ds as an arc length is always positive. However, reversing the orientation of a curve for f dot dr has the effect of changing the sign of f dot dr over c, right? So if I'm moving in an opposite direction, then the work should have an opposite sign.